Excellent. And we are back and we are ready for our first talk by Dr. Adam Dipert. And Adam, you are a physicist and a professional circus artist, and you're also the creator of the Space Juggler. You are a postdoctoral researcher at the North Carolina State University, and here you blend science and movement to explore how humans can perform and create in microgravity. You are a pioneering space juggler, which is a new performance discipline that is designed for weightlessness, and you use your work to inspire curiosity, creativity, and a sense of play in science outreach. Is this correct?
I think you got it.
Perfect. In that case, we are extremely excited to hear your talk. So please just take it away.
Thank you so much for the introduction. I'm really excited to be able to share this work with all of you today. I have been curious about what it would be like to have a circus in space, because when I think about possible states of the planet, the one that has dancers and circus people in space moving around it is a pretty cool version of our planet, and I'm into it. So I had some ideas about how to explore this, and those did not just appear out of nowhere. They did come from a bit of my own origin story, so I wanted to just run you through what kind of trajectory gets you to the place where I'm at. After I graduated high school, I ran away to join the circus, and I spent 4 years traveling around the United States and Canada, and I did not start college until I was 23. And it turns out that was a really good idea. Um, Once I got into college, I found out that spending all of those years manipulating objects with my hands and with my body really prepared me well for thinking about things in three-dimensional space and time. And when I was in multivariable calculus, I really got to see the mathematics that started to describe how I see the world, but in a different way. And this is a really fundamental component of the transition for me. Um, as I continued on in school, I ended up in graduate school, and my PhD is officially in astrophysics, but I did experimental nuclear physics, studying the baryon asymmetry. And what I found out was that using my hands was super useful when I'm working in a laboratory. And I discovered that all of those years working on my dexterity really helped for repairing equipment and building new pieces of equipment where a lot of my peers would be breaking our little tiny wires and things. And spending the time working with my hands ended up being really functional. And I'm mentioning this because some of the other people who I worked with who were the most skillful in a laboratory environment were actually mechanics and other people who had done things prior to going to college. So if you know people who are doing kind of labor jobs like that, that are technical, but maybe not the sciences, they still might have a lot of real useful skills to contribute, because it's going to be a while before we have, you know, artificial machines building everything for us, and we do still need to be able to do things with our hands when we're building real experiments. Um, I worked on nuclear magnetic resonance and helium-3, and it's a funny thing when you're doing it, because you take atoms' quantum spin state and then you tilt it over and then you put it in a holding field and they start oscillating. And some of the math can be a lot easier if you view the experience of your particles in the rotating frame rather than in the inertial frame, like their lab frame. And so you'll see kind of where I come back to this in the work as we're going forward. But I just wanted to seed that little thing that, like, I didn't realize some of the layers that can come out of just like learning to think in a new way. And in a manner, science and especially physics gives you an opportunity for really thinking outside of the box. And you just never know how it's going to influence you or make you or give you abilities and capacities that you never would have imagined. So, okay, looping back around, how to make a circus in space. So circuses need jugglers. Of course, that's not true. Circuses don't have to have jugglers, but they are a fundamental part of many circuses. And I started having curiosity about what it was like to have a body in a an environment without weight. And weight, we perceive to be like this experience of gravity, but actually, weight is the experience of resistance from a force against our bodies. And when we're not experiencing that force of resistance, what are the ways that the body turns? Becomes really important because orientation is a fundamental component of a body state. So, to describe some phenomenon about rotations that are actually very complicated. And I find most people, including people with their PhDs in engineering and in physics, do not understand actually in an intuitive way how rotations work. So I made this example that is uh, oop, is my thing going to play? There we go. Is a virtual reality simulation, but you can do this in reality with your own phone. It's just in the VR environment. You can see the phenomenon with uh, notation. So let's imagine this is your phone and it has three vectors around it, which all three-dimensional bodies do, that tell us something about how rotations work for these. Oh, geez, come on, play the thing. There we go. How rotations work on bodies, and they're always perpendicular to each other, and they're called the principal axes. So the blue axis we call the maximum, the red axis we call the minimum, and the green axis we call the intermediate. If you hold your phone in this red dot, where the red dot is at the bottom there, and you spin it so that like it spins around this direction, then what we can say is the angular momentum is going around that red line, which is the minimum axis. And if you throw it that way, it'll spin really stably, and we like things that spin stably. Now, if instead you hold it at the end where the red dot was on the side and you get it to rotate around the front face, angular momentum is now pointing toward the back there. Again, you get this like really nice stable rotation, and it's conceivable. Um, we can predict how this is going to behave. That's catchable in a juggler's situation. But what if you hold it at the bottom and you rotate it around the green axis so that it's spinning in this direction around the pink arrow? Again, that's the angular momentum. And you'll see that it starts spinning and it flips over. And this is a real physics simulation. I'm putting in the moment of inertia tensor, giving it an angular momentum, and seeing how the system behaves. And you can do this with your own phone in your own body or in your own environment with a couch or something so you can catch it safely. Now, if you throw it around some other axis, the motion becomes fairly complicated and it can be very difficult to track. So you can see now that it looks like it's rotating kind of around multiple vectors at the same time. If you understand the orientations of those, like the red and the green vectors, then you can see that the red vector is actually going in a circle. And this is one way to predict what's going to happen. Now, before I went on my first parabolic flights, I wanted to understand how this stuff influences my body. So I made a three-dimensional model of a human, and I tracked where all of these vectors are, as well as where the center of mass is when the limbs are moved around. And again, you can see the blue axis coming out of the body on the left, and then going horizontally, and the body in the middle, kind of at an angle, and the body on the right. And what I found so interesting was that I had never seen astronauts trying to spin around the blue axis, right? Even though that's like the most stable axis the body can spin around. And additionally, it's the only way your body can spin and always face in the same direction. So on parabolic flights, I really leaned into this. And whenever I go on a parabolic flight, I have a checklist, and this is always somewhere in it to try to figure out how to access this rotational mode from different positions. And on the right, you can see me doing it, at least for half a spin. Um, so the two basis ideas with how to juggle in space are one, that the human body can spin this way, and two, that when you throw a ball in weightlessness, the ball moves in a straight line because it's not affected by um, uh, linear gravitational force as we are close to the Earth. Obviously, it's still affected by gravity because there's gravity everywhere. And even when you're in weightlessness, you're still being affected by gravity. It's just that the ship is being affected by gravity just as much as your body is. So, in order to prepare myself for a parabolic flight, I built the apparatus that you see on the right, where I can hang myself over a table, roll the balls on the table, and then the top of it is attached to a swivel, and so I can spin my body around the blue axis and practice this technique. After I built the apparatus, the pandemic started, and I got stuck for 2 years with this apparatus. So I just worked on it a whole lot, spent about 700 hours in it over 18 months. I put a camera on the bottom facing up so that you can see the videos that you're going to see. And this is what it looks like when you film it from the bottom. And you can see that the balls are moving in straight lines as predicted. But once I saw this video, I started thinking, what would happen if I rotated the camera so that you could see the same thing that I'm seeing? And you notice that when you start rotating the camera, you don't see the straight lines anymore. You see these curves. And this is a good moment to back up and remember, I'm a guy hanging from a ceiling rolling balls on a table. But when we're looking at it, we see curves rather than straight lines. So this is what you would observe if you're operating in a non-inertial reference frame that is rotating. So, of course, I wanted to know what these patterns were. So I made simulations of them. And the left column are throws from the left hand. The right column are throws from the right hand. The left or the top row are catches with the left hand, and the bottom row are catches with the right hand. You can see left to left in the upper left uh, portion of the graph makes these interesting shapes, as well as the bottom right. Um, and the one that really captured my attention the most is the curves in the bottom left. I really wanted to know what was going on with those because they cross over each other, they change direction. It's really weird. So I was working in the rotating frame just like my atoms in the laboratory do. And I wanted an equation which represents my lived experience in a non-inertial reference frame. So this equation at the top is what I came up with. Omega 1 is the throwing hand. Omega 2 is the catching hand. Tau is the amount of time between the throw and the catch. Omega 0 is the angular velocity of the system. T is the time, and I is the imaginary unit. And so when I started playing around with this, I was like, oh, now I can see like really where I'm starting and where I'm ending um, in an equation. And as I was looking at this equation, I started noticing that it looks to me like an Archimedean spiral. And if you're really familiar with complex algebra, then you can probably see how I broke this down, that there's a bunch of constants other than the time t. Which are on the left-hand side of the parentheses. So I compress that all down to A, and then that right omega 1 is also a uh, constant, so we turn that into a variable b, and that maps an Archimedean spiral, which is this kind of spiral that just gets one step larger for each rotation. If you want to look at it in linear algebra, we can. This is what it looks like. Personally, I find linear algebra not to be the best tool all the time, and if you find curiosity about complex algebra or quaternions or Clifford algebras, I encourage you greatly to explore them because linear algebra is crippled when it comes to working with rotations. So let's look at what it looks like in the inertial frame when you throw a ball. It just goes in a straight line. But when you look at it in a rotating frame, it actually makes this like curve. And if it goes through the center like this, it does make the Archimedean spiral. Okay, so one of the curves that I was looking at definitely is an Archimedean spiral. But I was wondering, like, who else would be thinking about this kind of stuff? Because it can't just be me. And it turns out that people who are working on rotating spaceships would also be thinking about this stuff. So I found a paper by this guy, Ted Hall, who I since have gotten to chat with a lot. And he was actually considering what it is like to throw balls on rotating spaceships. And the phenomenon of ball motion on rotating spaceships is not like it is on Earth at all. And it's going to be really cool if we get rotating spaceships to see how things work in that environment. And as I started exploring, I started out with this this situation, and you see this person who's spinning here, and we're just going to drop the ball at first. And so you see, like when she lets it go, it travels in a straight line in an inertial frame. But then we're going to look at the rotating frame on the right side. And what Ted had observed was that this curve, when you drop a ball on a rotating spaceship, is actually the involute of a circle, which is a very specific mathematical shape. And once I heard that, I was like, oh, right, because involutes of circles and Archimedean spirals actually have something in common, and that is that they both can be generated by starting with a circle and then placing a line next to the circle, and then moving the line around the circle. So you want to move the line without slipping. If you start with the line or tracing a point that is attached to the line, then you get the involute of a circle. And that's the curve that you get on a rotating spaceship when you drop a ball. If you instead track a point that is offset by the radius of the circle, you get an Archimedean spiral. And that's what my mind was guided to by the equation. So then I wondered, what if we're just actually tracking all of the points that are slightly offset by different distances from that line? And sure enough, that is the full set of curves that we observe in space juggling as well as in all rotating spaceships whenever you're throwing a ball. And those curves are called roulettes. And other than that, they don't really have an official name. But here are some videos of tracking my thrown ball motions and then mapping the mathematical abstraction onto it so that we can see this underlying shape that is there. And when I started this, I talked to astronauts and engineers and a lot of people who told me there was nothing to find. We already have the equations. There's nothing more to see here. But I found something, and that's what I found. So you can see videos of it online. Dreaming of Space Juggling is kind of the main thing. And then I got a Nature publication for it. That describes the connection to rotating spaceships, and it goes into the math in a bit more detail. So if you're interested in the math, look up that article online. It is open source, or not open source, open access. But it could be open source if you, code the equations yourself and want to play around with them. Okay, that is my pitch, and I hope that you find your own place among the stars that is aligned with your curiosity.
This is so cool. You just asked if you're interested in understanding the math, and throughout the entire thing, I was like, I'm interested in understanding all of this. Like you mix between something that seems so everyday as, you know, throwing a ball, and then the mindfuck with the rotating the frame of reference, and this is really, really cool. Yeah, thank you. I would love to go see your publication. It looks amazing. So thank you very much for your talk. This was an absolute pleasure.
Thank you, Nana. It's really wonderful to share with you and everyone else this
Yeah,
evening.
it was great seeing it. Perfect. In that case, we will just take a minute. I don't know if Adam will maybe be hanging out at the exhibition afterwards, but you can try to go find him and ask your questions or not. Or if not, I'm sure you can go look up his webpage or write him an email if you have any questions. So thank you so much. We will just take 1 minute and then we will switch to Anya's talk in a bit. So thank you.